All right, we're in section 4.3 where we're going to prove triangles are congruent by SSS. SSS stands for side, side, side. And we have a postulate that talks about side, side, side congruency, which states that if three sides of one triangle are congruent to three sides of a second triangle, then the two triangles are congruent. So corresponding sides in this case, so if you look like, oh, we got hash marks at AB and we have hash marks at RS, those are congruent. And then we could say, well, CA has hash marks the same as PR, those are congruent. And then finally, BC and ST have the same hash marks. So since all three of those corresponding sides have congruent sides, we can then write in the congruency statement of triangle ABC is congruent to triangle RST. Okay, so the deal is when we're writing proofs and trying to confirm that triangles are congruent by side, side, side congruency, they all don't always give us all the information, but we have to be able to prove things by different definitions of things that we have looked at either again today or have looked at in past lessons. So we have a triangle, we have a diagram here, and the proof is they want us to prove that triangle FGJ is congruent to triangle HGJ. So we are given two things. We are given that G is a midpoint of FH, and they're telling us that FJ is congruent to HJ, which is illustrated by the hash marks in the diagram. So we have portions of our congruency statement. So this should be where the reasons go. And so we have the statements on the left, reasons on the right. And if we look here, we got G is the midpoint of FH. That's given to us. We also have another given statement here, which is step 3. So we can also say that FJ is congruent to HJ. That was another thing that was given to us. If you look here, they're telling us that FG is congruent to GH, so right here and right here. Well, the reasoning that those two are congruent is they told us that point G was the midpoint. Definition of midpoint means that they are equidistant from each endpoint. So by definition of a midpoint, those two line segments are congruent. So we have one set of congruent sides that were given to us. We have two congruent sides. That was by the definition of a midpoint. Now, our fourth step is a statement that isn't given to us, but the reasoning is the reflexive property. So reflexive property, again, is something that is congruent to itself. And if you look here, both triangles share this line segment of J. So we could say that like GJ is congruent to GJ because of the reflexive property. That is the third congruent side that we needed. And so now we can say that triangle FGJ is congruent to triangle HGJ because of side, side, side congruency. Here, they're asking us to decide whether the congruent statement is true. We need to explain our reasoning. So first things first, especially when they give us a diagram and they either give us actual measurements or they give us hash marks, we have to first make sure that the congruency statement that they give us is consistent with how it is lined up in the diagram. So if you look at this example here, they're saying us that triangle JKL is congruent to triangle MKL. So I look here and just right off the bat, I see that I have JL is 9 units. JL is points or letters first and third in the order of that congruency statement. And so ML is first and third in that triangle. So ML is also 9. So I can say that, yep, that works out. And then JK, which is 8 right here, that's first and second. Well, MK is also 8 first and second there, so that's good. So we found one pairing, we found two pairings that were the same. And then finally we noticed that LK connects both um, triangles, so that's part of the reflexive property. So I can say, yes, this is true because LK is congruent to LK by reflexive, and both triangles would be congruent by side, side, side. So looking at the second triangle here, they're asking us to prove if triangle RST is congruent to triangle TVW. So I have a hash mark right here for ST, that's second and third, and that means that I have VW, which is right here. Okay, so that's consistent. We have RT, which is 1 and 3, so T and W, which is also 1 and 3, that is consistent. But the problem is that there is nothing that illustrates a congruent line segment with RS and TV. So due to that, um, due to saying that we can't prove RS is congruent to TV, since we can't prove that, we can't prove RS is congruent to TV, so this would be false. Next thing we have here, we have a series of 3 triangles. We have triangles PQR, we have triangles VWR, and we have SRT. The question they're asking is they want to determine if triangle PQR is congruent to the other triangles shown on the graph. All right, so first things first, we have to be able to implement the distance formula in order to prove this. That's that x2 minus x1 quantity squared plus y2 minus y1 quantity squared. So we have to first figure out what the measurements are for the sides of PQR, and then determine using the distance formula with other triangles to determine if the corresponding sides equal the corresponding sides with PQR. Now with so we have PQ, we have looks like QR, and looks like we have PR. Now PQ is easy to find. We don't necessarily need the distance formula because we can just count 1, 2, 3. So PQ is 3 units. QR is another thing we can just count. We can say 1, 2, 3, 4, 5. That's 5 units. The only one we have to use the distance formula on is PR. So we got to find the coordinates. Looks like P is at 3, comma 1, 2, 3, 4, 5, 3, comma 5. And R is at, looks like 2, comma 2. So using the distance formula, I got Say it'll go 2 minus 3 quantity. This is actually, I'm sorry, this is negative 3. 2 minus negative 3 quantity squared plus 2 minus 5 quantity squared. So this is plus plus, 2 plus 3 is 5, 5 squared is 25, plus 2 minus 5 is negative 3, negative 3 squared is 9. And this gives me the square root of 34. And I can leave it like that because it's not a perfect square, and I'm just trying to look for things that are congruent for that. So first things first, I have my first and second letters in the triangle, so they have to correspond with PQ. So VW has to equal 3 in order for me to keep going forward with that particular triangle. So this is VW is right here. Looks like negative 3 comma negative 2 is that point, and looks like 0 comma negative 3 is point W. So using the distance formula, we're going to have what, 0 minus negative 3 squared plus um, negative 3 minus negative 2 squared. So plus 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 plus, 0 plus 3 is 3, 3 squared is 9. So I got 9 plus negative 3 plus 2 is negative 1, negative 1 squared is 1. This equals the square root of 10. Now the square root of 10 is not um, 3, so I can stop. So right off the bat, I know that it's not congruent because the first corresponding side that we chose didn't match up with the corresponding value of PQ, which was 3. Okay, so now we got to go and look at SRT. So first thing we're going to look at is SR. So if we look at that, actually I can just count this 1, 2, 3. Great. SR is 3. That corresponds with PQ. All right, QR is um, second and third, so I look at RT next. RT is right here, and that's counted as 1, 2, 3, 4, 5. Second one checks off. Now we gotta look at uh, so PR and then an ST. So ST is the next one, so we gotta check that one out. So point T is at 2 comma negative 3, and S is at 1, 2, 3, 4, 5, 5 comma 2 it appears. So using that, we're gonna have the square root of, let's look here, so what, 2 minus 5 squared plus negative 3 minus 2, square that. So this is going to equal the square root of, so it'll be 2 minus 5 is negative 3, negative 3 squared is 9, plus negative 3 minus 2 is negative 5, negative 5 squared is 25, and we have this as the square root of 34. So we can say by side, side, side congruency that triangle PQR is the only one that's congruent to is triangle SRT. Final thing in this section we're going to look at is stability. So stability here, it says they want us to explain why the table with diagonal legs is stable while the one without diagonal legs can collapse. So if you read here, it says that the table with diagonal legs forms triangles with fixed side lengths. By the side congruency postulate, these triangles cannot change shape. So since they cannot change shape, that table is stable. The table without diagonal legs, the one on the left, is not stable because there are many possible quadrilaterals with given side length. So there is a possibility that it could move and create different kinds of quadrilaterals, not necessarily like a rectangle that it appears to be, but it could move because there is not that fixed point. All right. Usually you need some kind of a diagonal to reinforce any one of these shapes to make um, it stable. So if you look here, um, we do have two shapes, and they want you to determine which one is stable or not. The first one here, since its fixed points are here and here, you can't move it. All right. These triangles are going to remain the same. So that's why this particular shape is stable, or this particular figure is stable. Now, our our points are here and here, which means that the inside here can be moved, and then these shapes here could also change. Since there's a possibility of those shapes inside there changing, this one is not stable. And that is being able to prove triangles are congruent by side, side, side. Hope this helps. Till next time.